So till now what we have done, if we have a quick recap on that, we have gone through some basics, that is actually before mid or before to be mid exam, which didn't take place, which is supposed to take place probably within 2 weeks. So the basics of uh, optimization, mostly classical optimization. Then we talked about ELD. Inside ELD, what are the variants that we talked? First of all, we talked about ELD problem constituted or formulated as an optimization problem with only equality constraints. So equality constraint problem. Next, we considered both equality constraint and inequality constraint, where actually we introduced the limits of the real power generation limits for each of the generating units under consideration. So this was another case. Third case was losses were included. That is basically the transmission losses plus equality constraints. And then we talked about the hydrothermal economic dispatch problem. So this was probably the last topic where we actually introduced the gamma iteration method. So probably some of us have gone through all of these topics. Some of us might not, but we can't wait because the mid syllabus will be actually up to this as declared earlier. So this would be the mid syllabus. Okay. So the syllabus of mid is not going to be updated, but we are going to continue with the course classes for these 2 weeks. So today what we are going to do, we are going to take the same ELD problem. We are going to consider the equality constraint, but we are going to solve this ELD having equality constraint by another technique, which is known as the gradient. In general, this is one of the gradient-based methods. Specifically, we are going to study the gradient descent method. Another name of this could be found in the literature, that is steepest descent method, all the same. If it is a minimization problem, we will go for the gradient descent method. So these are specifically for minimization problem. However, if it is a maximization problem, we can adopt similar kind of technique, but we will then call it gradient ascent method. So this is for maximization problem. Now, can anyone tell about what is a gradient of a function? Let's say, okay, just to make life easy, this is, let's say, x is the independent variable, y is the dependent variable. This is some function of x, single variable. So what is the gradient of this curve or of this function f of x? How do you find out the gradient? Anyone? Oh, no one is interested? Are you listening to me?
Yes, sir.
Atik. Okay, so I thought no one is there. Ghazi Fahmid. Okay, what is gradient? Anyone? Any of you?
So partial fraction করতে হবে।
Oh, partial fraction. অনেক দূর. Okay, that is one way, because actually we have only one variable. I wanted to make life easy for you, but you are going to the more complex domain. There are some guys, I am not audible. I will join again. Okay, no problem. If I am not audible to any of you, please inform me. But I think till now I am audible. So if at your end there is some individual problem, so you should log out and sign in again. Okay, I think that should solve the issue. So the gradient descent method, we should first know what is gradient and what is descent or ascent specifically. What is descent?
Am I audible now?
Yeah, you are audible. Now you are
স্যার
audible.
কথা বলতেছিলাম স্যার একটু আগে বাট শোনা যাচ্ছিল না
No, it was not audible. Sorry. Yeah, so can you define? Yeah, one of your friends said it is you should calculate some partial derivative. Partial derivative of
Yes.
what? Can you complete the answer?
স্যার del f by del x del f by del x plus del f by del y.
Oh, plus del f by del y. Actually, why is f?
Oh, not
Why?
y.
Okay, so why is f itself? Okay, this is in general, this is the definition. But fortunately, we have only one variable. It is not a vector of variable. X is a single variable. Okay, this is a single variable function that I am showing just to make life easy. So for a single variable, gradient is simply the slope of the curve. Okay, let's stay with the single variable. But for a multivariable problem, you have to apply the chain rule, okay, of differentiation. That is, you have to go for the partial derivative of the function. But here I'm taking only a single variable function, y equals f of x. So gradient is nothing but the slope of the curve or the function. But where? The question comes, the slope, if I choose this point, this is slope. If I choose this point, are they same?
No sir.
If I choose this point, it's completely different. If I choose this point, it's something else. So when you are saying that I'm calculating the gradient or I'm calculating the slope of a function, you have to define it in a complete manner. So let's say if it is a single variable function, dy by dx, then you should write something like that. X equals evaluated at some specific point. Let's say this is my x1. Okay, got it?
Yes,
So when
sir.
you say you are calculating the gradient, you have to mention that specific point at which you are calculating the gradient or the slope of the function. This is number one thing. So quite easily we can see that, well, here, what is the slope? Positive or negative?
Negative.
Negative. Here?
Negative.
Here?
There's no slope 0.
Slope is 0. Here? Positive. Here also positive.
Yes,
Okay.
sir.
Okay. But in general, we mean by gradient, by definition, gradient gives you the idea about this information that you say df by dx. Here, we always try to assume that df is positive as well as dx is positive. Okay. So in general, when we try to calculate the slope or try to say that calculate the gradient of the function at a specific point, so you are always try to refer to the positivity of the function or positivity of the value of the gradient. So the gradient, if when I say I am calculating, let me clear this curve and let me draw a fresh curve here. So if this is the function f of x, so now let's say if I want to calculate the gradient here at x2, let's say, so quite easily you can see that if I calculate df by dx, it will be some positive value. Okay, so positive change in x with respect to positive change in y, or vice versa. Positive change in y or change in y with the change in x. This is the by definition of this. Okay. So now, for example, you are calculating the gradient at this point x2 for this function. The gradient comes out as positive. Okay. So if you want to calculate, if you want to find out the value of x, or the value of, let's say, this is y1, this is y2, let's say this is x1 and this is x2, and let's say this is, for example, x2 prime. So how do you actually find out, or how do you relate y2 with y1 with the help of the gradient? I mean, how do you write y2 is y1 plus what? With the help of the gradient. Anyone?
dy2 minus y1 by dy.
Yeah, in that manner we can write y2 minus y1 divided by x2 minus x1 is equal to the slope, okay, equal to, let's say, the slope gradient. So simply I can calculate that x2 minus x1 into the gradient plus y1. Okay.
Yes, sir.
So in that manner, knowing the value of y1 as well as knowing these values, the gradient itself, the entries of x2 and x1, we can easily calculate the next value of my output variable of y. Okay. Because the gradient is positive, x2 is at higher value than x1 as shown from the figure. So it is expected that y2 should be at some higher value of y1. Got it?
Yes, sir.
Very easily, y2 is higher value than y1. Now, if we are interested, so my movement along the curve, will be in this direction, isn't it? If I say I'm moving from y2 to y1, sorry, from y1 to y2, I was at y1, I calculated the gradient at some arbitrary point x2 dash, and then I jumped from, I'm trying to go from y1 to y2. Okay. My slope is calculated as positive at x2 dash. My slope is calculated as positive at x2 dash. So if I am moving from y1 to y2, am I moving away from the minimum or moving towards the minimum? Away from the minimum. So in summary, what I'm trying to say, if I move along the gradient, I am actually going away from the minimum. Is it clear?
Yes, sir.
So if I'm trying to find out the minimum of a function, there are some conditions, of course. We are assuming that we have a unimodal function, or in simpler words, we have a function which has unique minimum. Okay. By that, what I mean, the function doesn't look like this. There are multiple minimums. Okay. This is the global minima. These are local minima. Probably I mentioned these things in one of the earlier classes. So this is multimodal function. Multimodal function. By multimodal, simply it means it has many minima. Okay, not a unique minima. So this is multimodal function. But I'm talking about unimodal function. We have a unique minima. So this, the pattern of the curve or the function that I have taken as an example, this is a unimodal function, unique minima. And that
is also applicable for positive gradient.
Yeah, I'm talking about positive gradient. Then I
Okay,
will come to negative gradient. This is positive gradient. Okay,
okay, sir.
this
Okay,
is
sir.
positive. So when I'm going in the positive direction, I'm saying if I move along the gradient is positive. So actually my solution points, my movement is taking me away from the minimum. I started from y1, but if I follow the gradient, which is positive at this point, then if I follow the gradient, I will move along this line, isn't it?
Yes, sir.
So that means this is the summary that will actually take me away from the actual minima, which is actually my target. So now if I, as Farhad was mentioning, if I come to the other side where the slope is different than this side, okay, what will happen? What is the slope here?
Negative slope.
Negative. So if I'm standing here, if this is my y1 now, and this is my, let's say y2, I'm trying to go to y2, this is negative slope. Okay, so this is y1. So we can see that similar kind of thing will happen because the slope is negative itself. If I follow the similar kind of relationship here, and if I try to follow the negative gradient, it will take me from y1, it will take me towards y2. Remember, the slope here is negative, the gradient here is negative. So if I follow the negative gradient path, it will not take me towards the minimum, rather it will take me away from the minimum if I follow the gradient, which is negative here. Are you getting my point?
Yes, sir.
Okay. So that means whatever be the nature of my gradient, irrespective of the nature of my gradient, if I am situated, I am standing at a certain point, be it this x1 or this x1, anywhere on the curve, if I'm standing anywhere on the curve, I calculate the slope or the gradient of the curve at that specific point. And my target is finding out the minimum of that function, specifically unimodal function, unique minima, global as well as local, both are the same. Then if I have to find out the minima, I have to go against my gradient. I have to go against my gradient. So in summary, to find the minima of a function, what I have to do, I have to follow simply two steps. What is the first step? Now, can you summarize? What is the first step?
To go against the gradient.
This is not the first step, because at the first step, you have to know what is your gradient, right? So
Yes,
you
sir.
have to calculate the gradient. This is the first step at a specific initial, we should say initial operating point or initial point. This is your step number one. Now, what is the second step? Go against the gradient. Are this point clear? These 2 points, because there are a few more points probably I will address after this. Any question about these 2 points? Why we are calculating the gradient, and why we have to go against the polarity of the gradient? You have to calculate the gradient because you have to know in which direction you have to actually move. Okay. Unless you know the direction of the gradient, you cannot actually decide in which direction you have to move. Okay. So unless you complete the step number 1, you cannot come to step number 2. So to decide your direction of movement, to decide on the direction of your movement, you have to first know what is your gradient. And that has to be calculated, of course, at a certain initial operating point, x1 or x0. Okay. Now, another question. Yeah, any question?
No, sir. So far, okay.
Okay. The next question is, how much should I jump? Okay. To find the minimum, how much should I jump? That is a very interesting, very, very interesting point. Let's try to see with the help of this diagram. How much should I jump? So let's see. Let's take the function again. Now let's say I'm here and this is my, let's say, x1, and this is say x1 prime on this side. Now, the amount of jump that I will make will decide my next appearance on the curve, isn't it?
Yes, sir.
I mean, how much am I going to travel following the inverse direction of the gradient or following the opposite direction of the gradient? How much should I cover in a single jump? Let's say if the jump is too high, then what will happen? If the jump is too high, then probably I will miss the minimum and directly I will come from here to here. Okay. Then again, there will be huge jump. Why I'm talking about jump, it will be little bit, it will be clearer little bit later on. Why this amount is important for us. Okay. The rate of jumping or the amount of jumping from one operating point to the next operating point. The next jump would be a similar kind probably, but with a reduced rate. So what will happen? Probably there will be some oscillation around your minimum if the jump is a little bigger than required. Okay, little bigger than required. So on the other hand, if the jump is too small, your steps are too small, then what will happen? It will take probably enormous amount of computing time to reach at the minimum. Are these two figures clear? What is happening?
Yes, sir.
If I'm jumping, I mean, like a rabbit, let's say, boom, 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 boom. I mean, it will be oscillatory around my minimum actual targeted value if the jump rate is too high. On the other hand, if I'm jumping too slowly, very small steps like a turtle or tortoise, then what will happen? Okay, I will ultimately reach my destination, but probably it will take very, very long time. Okay, many iterations will be required. So there is some optimum value. There is some optimum value of jumping, which would probably take me from this value to this value within a very few iteration. Okay, whose step size would be bigger than this but smaller than this, in between these two scenario. Okay, so this rate, this specific rate or the specific parameter that will define my amount of jump from one point to the next for finding the minimum or the maximum, whatever, that is known as the learning rate. Somewhere written as eta, somewhere as this eta or epsilon. Okay, but that parameter somewhere you might also see alpha. It doesn't matter, but the rate at which your algorithm is learning, the rate at which your algorithm is learning, in other words, we call it the learning rate. Okay, so step number 3 choose the learning rate, let's say we call it alpha or whatever, eta or epsilon, wisely. Step number 3. So now again come back to the naming of the algorithm. Why we call it gradient descent? Because we are looking for minimum. Descent means we are actually going against the slope. Okay, we are going against the gradient or against the slope calculated at a certain operating point. If we follow gradient descent, then we will reach the minimum easily. On the other hand, what is gradient ascent? Let me erase this. Remember, gradient ascent is the opposite of gradient descent. And also it helps us to find out the opposite value, that is opposite optimum, that is the maxima of a function, which might look like this. This is your y, this is your x. So now you calculate your slope here. You calculate your slope here, and you simply follow the slope. You go along the slope. Okay, whatever slope you get, you follow the slope. So that will give you the gradient ascent algorithm, which is simply the opposite of gradient descent, and that should take you to the maxima of the function. Okay, but we are not going to go into the detail of this, because this is just, I wanted to mention the name, that there is some opposite algorithm with respect to the gradient descency. So our main focus would be to study the gradient descent method or the steepest descent method. So we have talked about 3 things. The steps are, first, you can also choose this one at the first step. Choose alpha wisely, calculate the gradient at a specific initial operating point, and then go against the gradient to update the position of these points. Okay. Okay, so this is the basic, and now we are going to apply this basic to our ELD problem. Now, can anyone tell the drawback or any limitation for this kind of algorithm, gradient based algorithm? Anyone? Limitation with regard to applicability. Can you apply this kind of algorithm for, let's say,
Say any function with only constant value.
any function with a constant value?
Like if when you are going to calculate the gradient, it can be give us some infinite value.
No, if you take the derivative first, it will become 0, and when it will stay at 0 if you take the derivative all the time. Derivative of 0, 0, 0, 0, 0. Actually, if you have a constant function, there is no need to maximize or minimize it.
Right.
Okay. Now, anyone, any other example?
So multimodal function.
Okay. One problem with multimodal, there is another very tricky thing. Multimodal is still applicable, but what will happen with multimodal, let me show you. Now the multimodal, the problem with gradient descent, it's not exactly a problem, you can call it a limitation kind of thing. If the minima, you see there are many minimas, okay? There is many minimas. Highly nonlinear function. But still, we can assume it is a function because it is two-dimensional plot. So it is still a single variable function. Okay? So y equals f of x. But it is multimodal. So for the multimodal function, if we apply the gradient descent algorithm, what problem you might face is, if you start from here, if your initial x naught is this, and you start to apply your gradient descent algorithm, it will be trapped here. Okay, which is of course the minima, but a local one. If we start here, it will come down here. If we start here, come down here. All are, this is another local. Okay, if we start here, it will stop here, another local. It will only give you the global minima in this case if you start here or here. Get the idea? So for multimodal, it can still give you the global minima if you know the pattern of the function beforehand. Okay, you know that, okay, your global minima lies within this zone. Okay, let's say you can plot the function. You can say you can vary x plus and minus. Okay, this is your domain of x, range of x, and this is the domain. So you know that, well, if I choose my initial value here, then probably I can reach the global minima. So one way to find the global minima for multimodal function using gradient descent is, if you know the function beforehand, pattern of the function, you choose your x value wisely near the global minima. Or if you are lucky enough that you choose the initial initial value of your iteration, luckily you choose this one or anywhere here, then your gradient descent algorithm will yield you the global minimum, otherwise not. Okay, so still it can find some minima, be it local or global. It can give you some solution, but the answer I haven't got yet. What is the limitation of applicability? A big limitation. This is a limitation, but it is not a big limitation. You can still overcome it. Actually, the name, actually the answer lies in the name itself. How? The name is gradient, right? First step, you calculate the gradient. So if you have any function whose gradient calculation is not possible, means it is a discontinuous function. You get the point? Probably in the math courses, in some definition, you have found that, well, let's assume that function f of x and g of x are continuous and smooth. It means it is differentiable, or somewhere you might have found continuously differentiable. I hope you have found these terms in your one of the math courses earlier. So if your function itself, function f of x, is discontinuous or non-differentiable, means you actually cannot get the gradient. So in those cases, you cannot apply gradient descent or gradient descent algorithm. You got the idea?
Yes, sir.
But otherwise, it is a pretty good technique. Assuming the fact that you have chosen your learning rate, eta or alpha, whatever, pretty wisely. Not too big, neither too big nor too small. Okay. So now we are going to apply the gradient descent algorithm for economic dispatch problem. But why do we actually need to apply this? Another question should come to our mind, because we already know we apply the Lagrange multiplier method, we apply the Karush-Kuhn-Tucker condition for the inequality constraint, and we also know the gamma iteration method. There are many methods already available. So what is the essence of gradient descent algorithm in the field of economic load dispatch? It's already mentioned in the book. So if you go through the book, you will find it, but let me mention it here. In all the problems that we studied till now, we considered that our cost function, f of x or c of pg, right? Those were something like this. Alpha plus beta pg plus gamma pg squared, isn't it? So all of those functions that we assumed throughout our discussion before mid were taken as quadratic cost function. Okay, quadratic cost function. But not necessarily your function would always be quadratic in nature. You might find out that, well, for a certain unit or for a certain generating station, for a certain generating unit, you might come up with some function which are, of course, those should be differentiable for the application of gradient descent, but they are of higher order. Something like this. Okay, a polynomial of higher order, higher than 2. So if that is the case, then the methods that we have learned till now are not applicable. Okay, so if your if your cost function is more than quadratic in order, you have to go for some other techniques. Okay, one of the techniques is the gradient descent algorithm. Okay, this is the essence of why should we actually know the gradient descent algorithm for solving ELD problem. Okay, clear? Any question? Any question? Because we'll be jumping to the book now, into the book. So let me stop share. Okay, is the book visible? Section 4.7.2.
Yes, sir.
Okay, so this is the article that we are going to start. So now in the economic dispatch problem, so till now what I have mentioned is simply a function f of x, which is a function of a single variable. Okay, till now what I have mentioned, it is a single variable function, y equal to f of x, and I have shown the curve like this, very nice curve. So this is your y, this is your x. How do you find out the minima of that function using gradient descent? Now, when we are talking about multivariable function, then as you mentioned, as we started actually discussing, that you have to take partial derivative. So now we are in that domain. We are in the partial derivative domain. Okay. So once your function, the cost function itself, the f becomes a function of x1, x2 up to, let's say, xn, let's say this is your y, then if you say I need to calculate the gradient, then this would be the gradient. Is it okay? If it is a single valued function, simply you take this first one, df over dx, done. If it is a two variable function, you take df by dx1 and then df by dx2, done. Now, in general, if it is an n variable function, then you have to calculate up to the nth element of your unknown variable. Okay. Now, as I mentioned, the gradient del f always points to the direction of maximum ascent. Okay, that means the direction of ascent, climbing up. Now, if we want to find out, the maximum descent, of course, for the minimum, this is for the minimum. Remember, this condition is only for finding out the minimum of the function. So if I want to find out the minimum, we have to go along the maximum descent, and that's why we have to negate the gradient. So thus the direction of the steepest descent, another name of gradient descent algorithm, for minimizing a function can be found by the use of the direction of the negative gradient. Okay, already I have mentioned for a single variable function. So if you are starting from a certain initial point x0, then the new point x1 could be calculated using this. Okay, so x1 is equals to x0 minus epsilon into del f. Why there is minus? In general, what should we write? In general, we write x1, a new point, new value of x, where x0 is the previous value of x, plus del x, right? We can easily write very general, in general. So what we are doing is simply this del x means what? This del x means this is basically the gradient, the slope, or the change in the variable. So we are writing that we cannot go in the positive direction of the slope. So we have to go in the negative direction of the slope. So we negate this change in x, and we want to control our jump, the jump from x0 to x1 and onwards, from x1 to, let's say, the next value x2 and so on. Remember, these x1, x2 are not actually these x1 and x2. These are some points, okay? Some points of variable x. So don't get confused. These x1, x2, x3 are some value of x at certain iteration number 1, iteration number 2, iteration number 3, and so on. But these are the variables, x1 variable, x2 variable, and xn variable. So if I want to find out the next value of x, variable x, in iteration number 2, then I have to update it like this. So x2 is x1 minus epsilon, the learning parameter, into del f. Okay, where del f is the gradient, minus, because the descents, we have to go along the descents, not along the ascents direction, along the descending direction, not along the ascending direction. Okay, clear? Yes, no, very good. Any answer?
Yes, sir.
Yes. Okay. So the learning parameter epsilon will actually help us to control the jump from x1 to x2, from x2 to x3. Now there is another interesting point which I should mention here, and that is, let's say the question should come that should epsilon be a constant value or should it be a variable? Isn't it? Should we choose epsilon constant or a variable? Means, should we teach the algorithm at a constant rate or at a variable rate?
Variable.
Variable rate. So in two ways that could be achieved. Way number one, I am showing you now. How could it be a variable? So one thing is that either we can make epsilon variable, del f fixed. Okay, in that way, this portion, the second portion, epsilon multiplied by del f, this would be a variable. Okay, this is one way. Another way, keep epsilon constant and see whether del f itself is variable or not. If del f keeps changing in each iteration from one value of x to the next value, then we don't have to bother about epsilon. Okay, varying epsilon itself. We can keep epsilon constant and we can check, well, del f, whether it is constant or vary. If it is varying, then the whole thing would be varying in each iteration. So let's see. Let's go with, let's say, one of the ways where we treat epsilon as a constant, the learning parameter as a constant parameter. Then del f, remember, for a single variable, this is for a single variable function again, because multivariable, it is difficult to plot here. So I'm always going for an example, I'm taking help of the single variable functions. So let's say I'm calculating the slope here, which is positive. So I have to go against the slope. That means I have to come along this direction. Now, what is the slope here? Whatever value of slope is here, that is del f. When I am calculating slope here, is it same?
No.
No. If I'm calculating slope here, is it same?
No.
Now, is the slope decreasing or increasing?
Decreasing.
Decreasing, because the stiffness or steepness of the curve is actually decreasing. So that means del f itself is decreasing in each iteration when I'm jumping from one value of x to the next value, isn't it?
Yes,
and here
sir.
ultimately del f becomes 0. So I don't have to bother about varying epsilon itself. Rather, I can choose a single epsilon and I can stay with the del f variation. So when epsilon is a constant value, del f is changing for each x. So I'm already having a variation in this value, epsilon into del f. Okay, so I can stay with a constant epsilon, constant learning, but overall this change epsilon into del f is varying because del f itself is varying at each point of x, and it is actually reducing if I'm moving along this right direction towards the minimum. Okay, so these are a few important points while we are actually treating the gradient descent or gradient search algorithm. Okay, so now we apply the gradient method to economic dispatch problem. this is the old thing. Our target is to minimize the objective. There is the total cost function. So the total cost function, let's say if you have n number of generating units in the economic dispatch problem. So you have to take the cost function for n number of generating units and you need to add them up. So that will give you the total cost. So this is your total cost, okay, where Fi is the individual cost. The constraint, what is the constraint? As I said, the constraint, we are not taking the inequality constraint, but we are taking the equality constraint. And we are also not taking the transmission loss here because we already know how to deal with them, okay? Our main target is to look at the application of gradient descent algorithm for economic dispatch problem. So at least we have to take the equality constraint, and that is the summation of all the generation from all the units should satisfy the demand. Okay, this is old thing. These two are old things. Now, first of all, what we have to do, we have to make them a single objective. So we have to attach this equality constraint with the help of the Lagrange multiplier, and we have to rewrite this in this form, PD minus summation of PGI. So your Lagrangian would be F, original objective function, plus lambda, that is the Lagrange multiplier, multiplied by the reformed equality constraint. So now this becomes unconstrained optimization problem. So now we go to the first step of our gradient descent algorithm. What is the first step?
Calculating the gradient.
Calculating the gradient. How many variables will be here? Unknown variables. If there are n number of generating units, how many unknown variables for my optimization problem? Can anyone tell?
In number of
No.
variables.
Not exactly n. Why? It is partially correct, not completely correct. Is there any more unknowns here other than n number of PGIs? So one set of unknown is this, of course, PG1, PG2 up to PGN, okay? Because once we know the real power generation from each of the generating units, we are partially done. Why? Because in that case, we can calculate this, okay? Any more unknowns? If you check these three, anyone can identify?
So Lagrange multiplier to known.
How is it known? How do you know what is the Lagrange multiplier? You don't know, you have to identify. So your total unknown becomes n plus 1.
N plus 1.
Okay, n plus 1. So that's it. So you see this is unknown sitting over here. You don't know this. So you have n plus 1 number of unknowns. So when you calculate the gradient, how many entries will be there? N plus 1. Okay, n number of PG, PG1, PG2, PGN, and another one is with respect to lambda. Clear?
Yes, sir.
PG1, PG2 up to PGN, and then the remaining one is up to this is n number of unknowns. You are taking the partial derivative of L with respect to n number of PGs, but there is another unknown left here that is taken care of at this point of your calculation. So this is the total gradient. N plus 1 gradients are to be calculated because there are n plus 1 unknowns. So once you calculate it, what should you get in return? By now you should be able to do this. I mean, already we have 8 weeks of classes, not 8 weeks, theoretically 8 weeks, probably 5 weeks of classes have gone by. So by now you should be able to calculate this, that this thing gives you this thing gives you this thing gives you this, isn't it? Di L by di lambda. What is di L by di lambda? You take di L by di lambda. So what you will get? There is no lambda here. So there is a single lambda. So simply you will get this. So you see This is PD minus I equals to 1 up to n summation of PGI. So this is this thing. If you take dial by di PG1, so what do you get? Remember, there you have inside this you have PG1 plus PG2 plus to PGN. So all of the PGs are there. So when you're taking the partial derivative of L with respect to PG1, then this is also the function of PG1, function of PG2, function of PG3. So the first term is coming out of this block. The second term is coming out of this block. Okay. And all the same for all the other entries. You should be able to do this. Straightforward. So once you calculate the gradient, now you have to evaluate the gradient at a certain point. That is another important thing. You have calculated the generic expression for the gradient. That's fine. But you have to evaluate the gradient at a certain, to start the algorithm at least, you have to start from a certain initial operating point. So the gradient del L, that is the gradient of L, the Lagrangian, has to be calculated at a certain operating point. So let's say the initial operating points or the starting values are given like this: PG1 at iteration number 0, PG2 at iteration number 0, up to PGN at iteration number 0. These are n number of variables, and the remaining one is lambda, so that is lambda 0. So this should be given. Okay. So the problem setter should give you these values. Then the new values will be computed following the algorithm. This is the gradient descent algorithm in a single line. X of the value of X, that is the unknown vector. Here the size of X is n plus 1, remember. Here it is size is n plus 1. So X of 1 means it is the iteration number 1, or let's say after the initial declaration, the next iteration. So when you know the initial values, this one up to n, and then lambda naught, that means you know all these X naught. This is also the dimension is n plus 1. Okay. What is epsilon? Is it a vector or a scalar? The learning parameter or the learning rate?
Scalar.
Scalar.
It is a scalar. So you are calculating n plus 1, a vector of size n plus 1. On the right hand side, X naught, it is a vector of another vector of n plus 1 elements. Minus epsilon is a scalar. So what should be the dimension of del L? N plus 1. You already have it here. Okay. So these are the dimensions for each of the entries of your equation 4.103. Clear? Very easy. Nothing, no magic is here. Okay. So then they are explaining what is actually X1 and what is actually X0. X0 is already explained. This is X0, and X1 is all these values at the next iteration 1. So you will see PG1 of 1, PG2 of 1 when they write X1. Okay. PG1 of 1 up to PGN of 1, and then lambda at 1. The more general expression would be, so this is for 2 consecutive iteration. Okay, 2 consecutive iteration. In general, what you should do, it should be a function of the iteration number simply, where n is the number of iteration. So if you are looking for a value of the X vector at nth iteration, so you should take the X vector values at the previous iteration, that is n minus 1, minus, because of it is the gradient descent algorithm, epsilon, it is the learning rate, delta L, that is your gradient itself. Remember, delta L has to be evaluated at a certain values of all of your X variables. Otherwise, it is meaningless. The gradient is meaningless. The gradient or slope has to be calculated at a certain operating point. So what is the algorithm? Iterative algorithm. These are the steps. So step number 1, if we go through the steps quickly, select the starting values. So either you have to select it on your own, or the problem setter, the examiner, should give you these values. Remember, here there is no value of lambda. Okay. So you are only choosing the PG values to start with in such a manner that satisfies at least your equality constraint. Okay. You get the point? We already have used this kind of thing earlier. So let's say if your demand is 500 megawatt, you have 3 units. So let's say you take something like this, 150 plus 200 plus 200. Okay. Oh no, how much is it? It is 350. So another 150, something like this, or any other combination of PG1, PG2, and PG3 to start with, in such a manner that equals your demand. Remember, you don't have any limits on this, so you can also choose 0 plus 0 plus 500. Doesn't matter, as long as you are following this step. Okay, you can also choose 0 plus 0 plus 500. Doesn't matter. Clear? This is the initial step. I mean, if you have to choose on your own, you can also choose like this. But of course, an intelligent choice would be to give some share of load to each of the generating units. Don't keep them 0 at least, okay? Because they are running, so give them some load, arbitrary load, but keep this equation satisfied, keeping this equation satisfied. This is the equality constraint. Next, you compute the initial lambda I for each generator, lambda I for each generator. Be careful, lambda I for each generator. So if there are n number of generators, you are calculating lambda for each of the generators. Okay. So the lambda I 0 for I equals 1 up to n. So if there are n number of generators, you have n number of lambdas. If you have 3 generating units, there will be 3 lambdas. Okay. So lambda 1 0, lambda 2 0, and lambda 3 0. Why we are doing this? That will be clear in the next step. We actually want to find out some average incremental cost or average value of this Lagrange multiplier, because we actually don't know the exact value. This is one way to deal with this. Okay. To stay in the safe zone, you calculate each of their individual incremental cost and find out the averaging effect, the average value. Okay. So if there are 3 units, simply add 3 of them and divide by 3. That's it. That would be your lambda 0. And these are lambda 1 0, lambda 2 0, and lambda 3 0 for each individual generating units. Then we have the lambda calculated, the average lambda calculated, lambda for each generating units calculated. Initial values of PGs assumed. Now we are in a position to calculate the gradient, and this is taken as del L1. From where are we getting this? This is nothing but this equation 4.102. Okay, 4.102, which is already derived. So we are applying for equation 4.102 at step number 4, and this is your first del L1. Okay, so you are using the values. You see, you are using all the 0 values here, 0 0 0, all zeros, and using that 0, you are calculating the gradient for the next step, for the next iteration. That will help you to find out the new values of your unknowns. So what are the unknowns? PGs and lambdas. PGs and lambdas, these are your unknowns. So after you calculate del L for iteration, for the next iteration, after the initialization, this 0 means initialization. So after initialization, this is your first calculation of your gradient. You check whether all of the gradients are 0 or not. If there are 3 of them, then check whether all 3, there will be 1 2 3 generating units, so there will be actually 4, because this is n plus 1. Entries will be n plus 1. N plus 1 will be the dimension, because we have a lambda associated there. So 1 2 3 generating units. So for 3 generating units, you calculate this, and for the balancing of load, you have another one. So if all of these are 0, means you have reached the optimum. You will stop your iteration. Okay. If all of these are 0, you stop your iteration. Can you say why? I mean, if this is equals to 0, you get that this value is 0, this value is 0, this value is 0, this value is also 0. You stop your iteration and you take it as your optimum value. But can you say why?
Minimum reach হয়ে গিয়েছে, the slope 0.
Yeah, excellent. So the minimum from all directions has been reached. You see, a multivariable problem. So with respect to all of these unknown variables, the slope that is 0 has been reached from all angles. So that's why you see you get 0. So that means you have reached the minimum of the function. So that's why you should stop. Excellent. Okay. So, and if that is not reached, though, in that case, you have to update your PG values. Remember, you started from some arbitrary PG values. So you have got some gradient using those arbitrary PG values and some averaged incremental cost or averaged lambda. So now, if not, this del L is not equals to 0 means all of the entries are 0 within del L vector or array. If del L is equal to 0, the solution will converge. Otherwise, you continue to the step number 6. Now you have to select a scale lambda. Sorry, scale epsilon. That is a learning parameter or learning curve or learning factor, whatever you say, to handle the convergence rate, you can say also. With this epsilon, you calculate the new values of PG1, PG2 following equation 4.106. That is the basic of your gradient descent algorithm. So you know epsilon now, you know del L, you know xn minus 1. So you should be able to calculate xn. So this is the step number 7. And then once you have new values of PGs and lambdas, you go back to your step number 4. You don't have to go through these steps again because that averaged lambda 0 value has already been done for the first initialization step. So after the initialization is done, so then in the iterative loop, you should come back from step 8, you should come back to step 4. Okay, and this will continue until and unless this is satisfied. Okay, any question? Oh,
No sir, no questions.
okay. Okay, so now the problem is that another problem is left. It sounds good. Well, if this goes on and on, then we should get a solution. Life is very beautiful. But the problem is that because in most of the cases in numerical methods or the iterative techniques, the error that we are interested on, it rarely reaches 0, exactly 0. Okay, maybe it is 0.00002, and this is a vector of gradients. Okay, so let's say if there are 4 entries, let's say another one is minus 0.001, another one is plus 1 into 10 to the power minus 15. But theoretically, none of these are 0, isn't it?
Yes sir.
But for practical purpose, for all practical purposes, we can assume them to be 0. Very small value, very small value. It is pretty much more smaller than all these, but theoretically not 0. So you can relax this condition by introducing some margin here. Okay, let's say if del L is less than or equal to 0.0001, something very small value. Okay, the tolerance, some tolerance, you provided some tolerance so that your algorithm converges, solution converges within a finite time. Otherwise, it might take a pretty long time to to converge to the solution. Okay, this is the problem. So although in the book it says that take del L equals to exactly 0, I would suggest that don't go for 0, take some small value, okay, just as a tolerance, that when the del L value, all of the del L values, or you can also say like that absolute of del L, minimum of absolute, or sorry, maximum of absolute of del L is less than equals to this. So that will take care of all other elements. Okay. So you take the maximum of del L and absolute, that means it takes care of all the plus and minus appearing there within the vector. And that should be within a tolerance. So if the maximum value is less than this, means the minimum values are far less than that. So you are in a safe zone to say that your algorithm has converged to a solution. Okay. So in the next class, I will be going through the example. There are much more interesting things waiting for us when we start the solution of these problems. Okay. So any question? If you don't have any question, then I should quit. Before I quit, let us discuss on the class timing for the Friday's class. Because Friday I have to attend the office, and probably I won't be able to take the class on that time, on our scheduled time of 9:15 in the morning, because I have to attend 3-day office. So when I reach office, I have to do some official works, not the class. So any other day is suitable for you? Can you suggest any alternate day? Saturday is okay?
It is okay for me.
Saturday is okay, sir.
Okay.
This
then-
time, 8:15 or
Oh,
8:30.
Saturday this time, not in the morning.
Not in the morning, sir, because I'll be in
Okay,
office.
okay. So if you are, yeah, you have job. So okay, Saturday at 8:15, inshallah. This Saturday. Okay.
Okay, sir.
Okay. Thank you. So in Saturday, inshallah, we will be going through the example problems in an elaborate manner. Okay. So till then, stay safe, and we should pray for each and every one so that we can stay safe. Okay. Assalamu alaikum wa rahmatullah.
Assalamu alaikum.
Wa alaikum assalam.